Hey everyone, welcome back. This will be part B of lecture 14. We're going through the topic of differential equations, separation of variables. Okay, so I want to do one more example before we jump into the more complicated separation of variables scenario. All right, so let's do this example. So find the equation of the curve . Find the equation of the curve that passes through the point uh, 1, 3, okay, and has a slope of y over x squared at the point xy. Okay, so this is kind of an oddly phrased example, and that's by design, right? So we're trying to phrase things in different ways and kind of make sure our thinking is sufficiently loose around some of this stuff, right? So because the slope of the curve, it says, is given by y over x squared, right? We know that that must be the derivative, right? So because the slope of the curve is given by y over x squared, we know that y prime equals y over x squared, right? So that's kind of the cloaked language, okay, right? So, cloaked, it's not cloaked. That's sort of, kind of a funny way of saying that the derivative y prime is equal to y over x squared, right? You just have to know that little bit from Calc 1 that, of course, the slope of the curve is given by the derivative, right? And we're also told that the curve that we're looking for passes through the point 1, 3, okay? So because the curve we are looking for passes through 1, 3. That's an initial condition, isn't it? Right? That's an initial condition. So because the curve we are looking for passes through 1, 3, we know that y of 1 is equal to 3 is an initial condition. Right, it's going to help us narrow down, well, which curve are we talking about? There could be an infinite number of curves that have this as its derivative. Which one are we looking for? There's only going to be one that passes through this particular point and has that derivative. Okay, so let's go find the curve. Right, so we start with dy dx equals y over x squared. This one is actually really easy to separate, right? This is maybe a one-stepper. Even we could just basically divide both sides by y and multiply both sides by dx, and so we get dy over y equals dx over x squared. Okay, so we can integrate both of those. Okay, and how we do that? Well, this is the natural log of y. Okay, and this over here, this is really x to the negative 2 power, right? So you could write that as x, the integral there would be x to the negative 1 over negative 1, okay, plus the constant. Okay, and so maybe better to write it as the natural log of y equals negative 1 over x plus c1. Write it like that. And then we can get rid of the natural log by just saying e to the ln of y equals e to the negative 1 over x plus c1. Right, and then what happens? Well, this old trick here of y equals e to the c1 times e to the negative 1 over x, which implies that y is equal to c e to the negative 1 over x. Right? So this would be kind of like the best, this would be sort of the general solution. Right, so this would be the general solution, but then what is the particular solutions? Because remember, we're looking for the curve that passes through a particular point, right? If C, depending on what C is, this is going to pass through lots of different points. It may or may not go through 1, 3, depending on the value of C, right? So we need to figure out what C is. So then, because y equals 3 when x equals 1, we can determine what C is. So that would mean that 3 equals C e to the negative first power. So it would be negative 1 over 1. And so that means C is equal to 3 divided by e to the negative 1, which is 3 times e, which is, well, let's leave it like that. You can obviously calculate this and approximate it, but let's just leave it like this. So C is this very specific thing, and so that means y equals 3e times e to the negative 1 over x, right? That's going to be the particular solution, and we could clean this up, right? This is e to the first times e to the negative 1 over x. And so we could write this as 3e to the 1 minus 1 over x. Or we could write it as y equals 3e to the x minus 1 over x. Maybe that's the best way to write it. Okay, so that is our particular solution, right? So if we were to plot this curve, y equals 3e to the x minus 1 over x, then it would have a slope of y over x squared everywhere, right? The first derivative is y over x squared, and the curve would pass through the point 1, 3, right? So it would satisfy all of the conditions that the problem is asking for. Okay. All right, very good. Now let's talk about examples where separation of variables are not straightforward, or not as straightforward for sure, and we need to employ some tricks. Okay, so this is going to be homogeneous differential equations. All right. So some differential equations may not be separable in terms of x and y. Right. So sometimes you'll get a differential equation and there's no way to separate x and y. But there are tricks we can do to make them separable. Right. So we may be able to change variables and create a separable differential equation. So let me write all this down. So some differential equations that are not separable in x and y can be made separable by a change of variables. Okay, so this is true. So this is the scenario that we encounter for differential equations of the form. So this is true for diffie-q's of the form y prime equals f of x, y, where f is what's called a homogeneous function. Okay, right, so the form here is y prime equals f of x, y. All right, so we just saw examples where, we had a form where you had m of x plus n of y times y prime equals 0. Right, so in this case, differential equations of this form are immediately separable, right? So m of x can just come over here, n of y can stay here, and dy over dx can can split as needed, right? So these are immediately separable. Okay, easily separable, right? And then we saw some examples also where, you know, maybe the differential equation isn't given exactly in this form, but we can do some things to it. We can multiply by this, divide by that, switch some things around, do some factoring, whatever, some kind of simple algebraic manipulation, and we can convert it into this form. Okay, so those are the two things we saw already. Now, what happens if you have a differential equation that is of this form that just isn't separable in terms of x and y, right? You can't get all the x's on one side and all the y's on the other, and the dx on the same side and the dy on the other side, right? So if this is not separable, right, in terms of x and y, it may still be separable after a particular change of variables. But in order for that change of variable approach to work, f needs to be homogeneous. Okay, now what the heck does homogeneous mean? All right, so let's talk about what homogeneity means when we talk about a function. So a function f is homogeneous. Okay. So a function f is homogeneous of degree, let's put that in quotes, that's what we're talking about. A function f is homogeneous of degree n if f of tx, ty is equal to t to the n times f of x, y, for some n. Okay. So what does this mean? Well, it means if I take the function and I plug in t of x instead of x, and I plug in t of y instead of y, then I ought to be able to factor all of the t's back out of the function and get this expression, t of n, t raised to some power times f of xy. Okay? So this is the sort of definition of a homogeneous function of degree n. Okay, so this is all very cryptic. Let's do an example, and I think the idea will be clear. Right? Let's start with this example. F of xy equals x squared y minus 4x cubed plus 3xy squared. Okay, so this function here is homogeneous and of degree 3. And why? Well, because, let's do it. Let's do the exercise here. F of tx times ty, right? So everywhere you get an x, you got to plug in a tx now, right? So tx squared times ty minus 4 times tx cubed plus 3 tx ty squared. Right, so just everywhere you got an x, now you got a tx. Everywhere you got a y, yeah, you now have a ty. And so that's equal to t cubed x squared y, right? Notice here you get a t squared, there you get another t, so you got t cubed here, minus 4 t cubed x cubed, right? So t cubed x cubed, plus 3, and now here you're going to get a t cubed again, so you got 1t, and there you're going to have 2, so altogether you have t cubed times xy squared. Okay, so the whole thing can be written as, you can factor a t cubed out of each term, right? And you get x squared y minus 4x cubed plus 3xy squared, right? And so that's equal to t cubed times f of x, y. Okay, and so f of tx ty is equal to t cubed f of xy, and so this is homogeneous because of that property, and it's of degree 3 specifically because of the t cubed that you see up front. All right, let's do another example. Let's say f of xy equals x times e to the xy plus y times sine of y over x. Okay, let's check let's determine if this is homogeneous and if it's and what the degree would happen to be. So f of tx ty is equal to t times x e to the tx over ty plus ty sine of ty over tx. Okay, and so here you're going to have a t out front. These two will cancel, and so you just are left with x e to the x over y. Same thing here. You'll have a t out front, and then you're left with y sine of y over x. And so, of course, you get t times x e to the x over y plus y sine of y over x, which is t times f of xy, right? So this is homogeneous of degree what? 1. Okay, now some functions don't allow you to do this. Some functions do not have this property. Right, so let's see an example there. What about this guy? F of xy equals x plus y squared. Well, f of tx comma ty, that would be t times x plus t times y squared, right, which is t of x plus t squared y squared. Now, I can't get a t out of both of these. It just doesn't work, does it? Right, so this is not equal to t of n times f of xy for any n. Okay? So that's the situation. Okay. All right, so then given a differential equation being homogeneous, let's now we have a description of homogeneous. Let's go ahead and talk through what we can do with this. Okay, so first we need a definition of kind of a more strict definition of a homogeneous differential equation. A homogeneous differential equation is an equation of the form m of xy dx plus n of xy dy equals 0, where m and n are homogeneous functions of the same degree. Okay, all right, so a homogeneous differential equation has this form. You've got m, a function of x and y, times dx, plus n, a function of x and y also, times dy is equal to 0. The key here is that m and n are both homogeneous functions and they have the same degree, right? So if this is a homogeneous of degree 2, then this needs to also be homogeneous of degree 2 in order for it to be considered a homogeneous differential equation. Okay. All right. So let's do an example here. So definition, example, definition, example. So let's say we have x squared plus xy times dx plus y squared dy equals 0. Okay, so we want to say that this is our m of xy, and this is our n of xy. Okay, and what we need to confirm is that this and this are both homogeneous and have the same degree. So let's start with the m function. Right, so that's going to be t of x, quantity squared, plus t of x, t of y. And so, of course, you're going to get t squared x squared plus t squared xy, so you get t squared m of xy. Okay, so this is homogeneous of degree 2. We can kind of see that n is going to be the same way, isn't it? N of tx, ty will be ty squared, which is t squared y squared, which is t squared n of x y. Okay, so degree of m equals the degree of n. Okay, so that means this is a homogeneous differential equation. This guy up here is a homogeneous differential equation. Oop, I'm running out of ink. So that guy up there is a homogeneous differential equation. Okay, right, it obviously fits the form mxy times dx plus nxy dy, and m and n are both homogeneous of the same degree. Right, so it has all of the features that you would require of a differential equation in order for it to be homogeneous. Here's another example. X cubed dx equals y cubed dy. So is this a homogeneous differential equation? Yeah, this one we can see, right? We can see for sure if we plug in a tx here and a ty here, then we're going to get a t cubed factor for both, aren't we? Yep. So this is homogeneous of degree 3. Perfect. Okay. What about this example? X squared plus 1 times dx plus y squared dy equals 0. Okay, so let's see. Is this a homogeneous differential equation? Well, let's call this our mxy, and this our nxy. And so m of tx, ty would be tx squared plus 1, which is t squared x plus 1, which, there's, again, you've got two terms here, and t is not in both terms, so you can't factor a t out, or a t squared out in this case. So this is not equal to t of n mxy, right? So this piece of it, this m is not homogeneous, right? And so that's going to mean that the whole thing is not homogeneous. This piece of it over here is, however, right? You can quickly see that this is going to be ty squared equals t squared n of xy, right? So this one is homogeneous. This one is not. So the differential equation is out. Not a homogeneous differential equation. Okay. All right, so that's sort of the starting point. Now we need all of these definitions, all of these examples, in order to apply this very slick method, right? And here is the very slick method. Okay, so if m of xy dx plus n of xy dy equals 0 is a homogeneous differential equation, okay, then it can be transformed into a separable differential. Well, it can be transformed into a differential equation whose variables are separable separable by the substitution y equals vx, where v is a differentiable function of x. Okay, so how does this work? All right, we're going to do it. We're going to do a nice example here. Okay, we're going to do an example. So it's kind of a longer example, but that's just because when you have to use this method to do separation of variables, then inevitably, well, not always, but often the differential equation is just somewhat more complex, right? So let's go ahead and let's try to find the general solution of x squared minus y squared times dx plus 3xy times dy equals 0. Okay, so we'll just say that this is our mxy and this is our dxy. We need to confirm that they're both homogeneous and of the same degree. And so let's do that. So m of tx ty is tx squared minus ty squared, which is t squared times x squared minus y squared, right? So you can see that. And so that's t squared mxy. Okay, so just plug those in, do the factoring, and let's check the other one. And so that one is going to be 3 times tx times ty. And so that's t squared times 3xy. And so that again is t squared times n of xy. So both of them are separable and they have the same degree, right? So you can see they're both of degree 2. Or sorry, they're both homogeneous and separable of degree 2. Okay. Sorry, they're both homogeneous of degree 2. Okay. And so that means that we can apply this substitution. This theorem says that we can substitute in y equals vx. So let's let y equal vx. Okay. Then dy is equal to, now this is the chain rule, so it'll be x times dv plus v times dx. Okay, so this is kind of the substitution that we're going to apply. All right, and so basically we're going to end up with a function of x and v. We're going to get rid of the y's, right? Y is going to become vx, and it's going to, this is the substitution scheme. Okay, so away we go. And then so once you've done this, then it's a matter of, doing a lot of algebra, separating things out, integrating, and then resubstituting your original variables back in. Okay, and so let's do that. Let's say we have x squared minus y squared times dx plus 3xy times dy equals 0. Okay, and so instead of y, we're going to have vx. Instead of dy, we're going to have this. So we have x squared minus vx squared dx plus 3xy times dy, which in this case is going to change to x dv minus v dx. And that's equal to 0. Okay, so now we just expand everything. Okay, do all of the expansion here, and we would have x squared dx minus v x squared dx plus, and then this will expand here, so it'd be 3x squared y dv, that's this, and then the other two as well, minus 3xy, oops, oh shoot, shoot, right here I wanted to put a vx in, so let's just do that quick, sorry about that. That's a vx, that means that's a v and an x cubed, and then this is a x squared v. Okay, and it's actually v squared, and then finally plus, let's see, plus 3x. Okay, I'm sorry, I'll just have to start over. It'll get too messy otherwise. Apologies for that. You make kind of one mistake and then it sort of all goes south on you. So it's x squared minus vx squared times dx, right? Just plug in the vx there. And then it's plus 3x vx dy. Nope, not dy. It's x dv plus v dx. Okay. Sorry, that got really messy. It's actually not that tricky. I just wasn't paying attention and I didn't do it right. So, okay, now we go ahead and do the expansion, right? So this would be x squared dx minus v squared x squared dx, right? So that's just this piece. Expand it all out, distribute, and then this piece here. So this is really 3x squared times v. And so when I multiply that here, I get 3x cubed v dv, right? So that's these two. And then the last one is going to be 3x squared v squared dx. Okay? And that's equal to 0. Okay, sorry about that. It was probably just easier to start over with that one. All right, not a problem though. We're still doing fine. All we're doing is distributing and expanding things. There's nothing tricky yet. Okay. So now we want to kind of do some grouping. So we're going to group some of these terms together. I'm going to take the x squared dx. Okay, and then I'm going to take the v squared x squared dx. So this next one. And then I want to take the last term, plus 3x squared v squared dx. Now why am I, and then this one will be on the end here. Why am I doing that? Well, I want to kind of think of those as being together because that's where the dx factor is located. And so we can factor all of that out and do some combining too. So this is x squared v squared, this is also x squared v squared. So I get x squared plus 2v squared x squared times dx plus this thing over here, which is 3x cubed v dv. Okay. All right. Okay, so then factor out the x squared here. So I get x squared times 1 plus 2v squared dx plus 3x cubed v dv. Okay, these are all obviously chain of implication here. And so then I can do some separation, right? And so we'll move this guy to the other side of the equation. So x squared times 1 plus 2v squared dx equals negative 3x cubed v dv. I can obviously factor out an x squared and cancel it. All right, so that means I have 1 plus 2v squared dx equals negative 3 v times x, or x times v dv. Okay, and so then I can just do some separation here, right? Right, so divide both sides by x, and I get 1 plus 2v squared dx over x equals negative 3v dv. And then also divide both sides by 1 plus 2v squared. and I get dx over x equals negative 3v over 1 plus 2v squared dv. And voila, right? We have a separation here. So I've got all the x's on this side. This would be like my mx. And over here, I've got all the v's. This is like my nv, n as a function of v. Okay, and so that means I can integrate now. Okay, so the integral of 1 over x dx will be equal to the integral of negative 3v over 1 plus 2v squared dv. Okay, this one is straightforward. It's natural log. Over here, we're going to have to use a u substitution. So u equals 1 plus 2v squared. Then du is equal to 4v. Right, so that means du over 4 equals v. Oh, dv on there. Okay, so that's kind of a side calc. And so let's rewrite it with the substitution in place. And so I get, let me see here. Yes, this would be negative 3 over 4 times the integral of 1 over u du. Okay, and so that means this is the natural log of the absolute value of x, and that's equal to negative 3/4 times the natural log of u, which is 1 plus 2v squared. And we'll throw the constant in there. All right, so let's see if we can work this out. So multiply through everything by 4. Okay, like so. And then we get, I'll switch pages here, no problem. Just switch pages, and we get the natural log of x to the 4th is equal to the natural log of c times, let's see, 1 plus 2v squared to the negative 3rd power, right? So kind of bringing some of these things together. And that means, and then we can use the e to the ln x to the 4th equals e to the ln of c 1 plus 2v squared to the negative 3rd power. And so that means x to the 4th is equal to c times 1 plus 2v squared to the negative 3rd power. And then the last step, of course, is we don't want the v, we want our original. So remember we said that y is equal to vx, and so that means v is equal to y over x, and so we can plug that back in. And we get x to the 4th equals c times 1 plus 2 times y over x squared, and that's raised to the negative 3rd power. Okay, and so this would be the solution to this equation. Okay, so yeah, I know that was kind of a heavy one, but the trick is, right, to use this. The trick is to substitute y equals vx and dy equals vx. Let's see, make sure I use the same notation. I want to write it exactly the same. So x dv plus v dx into the equation, and then separate with x and v, and then do the integration, and then plug everything back in. Okay, so let's see, we can do one more example. Let's take about 5 more minutes. We'll do one more example. So find the general solution to y prime equals x plus y over 2x. Okay, and so let's see, can we separate this? Well, it's not easy to separate, right? So dy over dx equals x plus y over 2x, right? So you can kind of see you get 2x dy equals x plus y dx, right? So it's not obvious how this would be separable. And so let's just confirm that it's homogeneous and try this. Let's confirm it's homogeneous and then try to use the y equals vx substitution. So let's see, this is homogeneous over here because of course tx, you can factor the t out, and this is also homogeneous. You're going to factor out a single t. So this is a homogeneous diff EQ of degree what? 1. Right, you can just kind of see that. You can see the structure here is gonna yield a homogeneous equation of degree 1. And so let's do the substitution. So let's let y equal v of x. Then dy is equal to x dv plus v dx. Right. So this is our innovation here. And so here's what we have. So we have 2x dy equals x plus y dx. And so let's do the substitution. So 2x times, and then it's x dv plus v dx. That's this part. And that's equal to x plus y, but instead of y, we're going to put vx dx. Okay. So we get to that. And then, as per usual, we're going to go ahead and expand everything and regroup. So we've got 2x squared dv plus 2xv dx equals x dx plus vx dx. Okay, let's get all of the dx's on one side and all of the v's on the other. And so I'll bring this guy over here. So 2x squared dv is equal to x dx plus vx dx minus 2xv dx. Right, so like terms. So these two are like, right, those two are like, and then the other one is kind of stuck out there by itself. And so I get 2x squared dv equals x dx minus vx dx. All right? I believe so. Okay, and so just thinking about this part here, and over here, let's factor out the dx. I get x minus vx dx, and I can factor an x out of that. And so I have 2x squared dv over here, and then I have 1 minus v times x dx over here. And so we can see what's going to happen. So it'll be 1 over 1 minus v dv, right? And that'll equal x over 2x squared dx. And so what do we get? Well, in the end, we're going to integrate 1 over 1 minus v dv, and we're going to integrate 1 over 2x dx. All right. And so in both cases, you're going to have basically a natural log. We're going to use the natural log, right, to integrate both, or to do the integration in both cases. And so we get the natural log of 1 minus v is equal to the natural log of 2x plus some constant. Okay, let's go ahead and plug back in the x and y's for v. So v was equal to, y was equal to vx, and so that means v is equal to y over x. So we have the natural log of 1 minus y over x is equal to the natural log of 2x plus the constant. Let's exponentiate both of these. So e to the ln 1 minus y over x equals e to the ln of 2x plus c1. Okay, and so that means we've got 1 minus y over x equals, what's it going to equal? Well, this will be e to the c1, and this will be e to the ln 2x, and so it's really just going to be c times 2x. Okay, and we can kind of clean this up a little bit. Let's write this as x minus y over x equals c times 2x, and we can We can kind of group those. C times 2 will just become a new C. And let's multiply everything by x. So we get, in the end, we get x minus y equals cx squared. Okay? And that would be the general solution. All right. So that is basically separation of variables. Okay, so I know that was a very kind of a longer lecture, but that's the basic methodology for separation of variables. And for, in particular, the easy case that we talked about more in the first lecture, and then the harder case where you can't do an easy separation, but you have to rely on this y equals xv substitution. Okay, and so in a normal differential equations class, you'd usually start with this, and then you would jump into, you kind of take this and move on into what are called first order linear differential equations, and kind of a general solution for that type. And then you move on to another type, and then another type, and then you would get into the Laplace transformation, and then you would do other things as well. And so that's all going to be part of the differential equations course that'll be coming up. Right, so that's where we're going to end our investigation of differential equations. Again, just a preview of what to expect from that subject. Okay, so it's a lot of this kind of stuff, really tricky algebra, kind of basic, more basic integrals, but very, some of the algebra can get really tricky and kind of involved. Okay, so that's where we'll leave it, and then when we come back next time, we'll get into we'll start talking about new and different integration techniques, things we haven't seen. So see you all then.